Of course, we also say that from the very end, that's something else. And of course, we have to say thanks to Pawel Dlotko, coming all the way from Warsaw, this conference. As you may know, Pawel is the director of the Dioscuri Center in Topological Data Analysis. I had the opportunity to visit this center that January. And by the way, I met Dlotko 2 years ago in Paris. Probably was 2015 or something. When he was a young guy.
I must say I just so
Okay, so I think start to start. I insist, I really appreciate you're here. So Pawel, take it away.
thank you very much, Carlos. Thank you for the invitation. It's fantastic to be here with you in Mexico, in Merida, and to be able to meet old friends, to make new ones. And, that's a closing talk. So I want to kind of wrap up a little bit on the data analysis. So as Carlos mentioned, I'm Pawel Dlotko. I have the privilege to lead in Warsaw with this institution, which is Dioscuri data analysis. And I will tell you about some part of the work that we are doing together. That's better. Thank you. So where we apply topology. And it was probably maybe the simple first when I actually read Alexander Solzhenitsyn. He was famous Russian author, the laureate of the Nobel Prize. But in the 20s and 30s, he was actually studying in St. Petersburg mathematics, to be precise, topology. As you can see, he wasn't very enthusiastic about the possible application of topology. And even nowadays, if you speak to topologists, that you just enter a random room where discussions about topology are taking place, you would expect to see a playbook like this. Doesn't look quite a lot. However, there is a small something growing, as we see in this conference, subcommunity, which we call the topological data analysis. And in our case, this is how topology may look like. So over here, that's actually one of the main pictures from a famous paper by Dana Carson and 2011 PNAS. What they did was to look at very, very high dimensional, so essentially 2000 dimensional data set of breast cancer data. It was NKI data set, something very well explained. So essentially everything there was in the toolbox of data analysis, probably somebody has tested it on this data. But what was the unique thing Gunnar and Tom found was that subgroup of breast cancer patients, roughly 20% of patients with 100% survival. They were able to identify 3 genes that are responsible that kind of place the patients in this area. And after this conference, after our session, and hopefully also after my talk, I would like you to think about topology not only by that image, but also by this image. There's a potential that can be really useful in the end. Okay, so topology data science. There's a single reason why I think topology may be useful in data science. It is invariance into some information. That's a classical thing. We also saw it in the previous talk, but one before. When it comes to classical topology, Horus is equivalent. And well, there are two ways you can understand the message. First, you can sample case, you can understand it negatively, and tell that we cannot tell this apart, which is by the way not exactly true, because most of the environment, the topological data analysis, they do take into account geometry. And once we do, we very much can distinguish copy mapping the problem. But we can also take this message positively. And what happens over here is, well, essentially every real data is corrupted with some sort of noise. The noise can be understood as continuous deformation of data. So our brains are very well good in kind of capturing the underlying shape of the data, even in the presence of huge considerable deformation. And what I will try to convince you is that topological data analysis and the variance we have also are able to capture the underlying information also in the presence of large corruption. That's the level of one of the functions. And of course, topological data analysis is not the first branch of mathematics that is dealing with data, is trying to understand quantum data, for instance, go very beyond that. Of course, standard statistics is providing a rich toolbox to assign certain data sets with a certain shape, some characteristics. Those characteristics sometimes are real of the shape. However, statisticians are well aware that they may be missing something. So what you are doing typically in statistics, you will have a data set like this. So for some reason in statistics they call it sample. In machine learning, topological data analysis, we call it point count. That means exactly the same. Since I'm thinking about statistics, I have such a sample. What can I do with it? Well, I can take the x value and compute the average x value, the same for the y values. Okay, once I have an average, I can compute standard deviation. Maybe I can compute the correlation between dimensions. Since those are two data sets, I can also compute non-linear regression, solve the mean square problem, and find the line that fits this data set best. And what Scuba realized already in 73 is that if I do all of those operations, so average x, average y, standard deviation x, standard deviation y, correlation between dimensional are almost exactly the same number for all those four data sets. So if you compute what I will call the summary statistics, those data sets will be indistinguishable. The reason for that is that you are compressing already quite a lot of information into a single number. And the higher dimensional your data set is, the most drastic is compression. So this was 73. That's more recent data. Our data set, I think, is 2016. And all those data sets that you see, including the dinosaur, the T-Rex over here, have the same property, the same average standard deviation over axis, the same correlation between dimensions. Yet, very different shape. So, in statistics, they say always visualize. Easier to say than done. I mean, you can visualize scatter plot if your data happen to have two dimensions. That's not often the case in real application. So that's what PDA is coming from. So if you ask what PDA have ever done for us, there are, I think that's kind of a recurrent motive, two main branches. The topological visualization tool, aka Matter type algorithm, and also ways of assigning feature to describe the shape. I like to think about it as statistics. So we compute some algebraic invariant, some functional invariant of the data. That we should think about it as an average or standard deviation, but it contains more information. That's what we are going to do. And since there are two main working processes of topological data analysis, are actually, probably everybody is doing nowadays with artificial intelligence, running ChatGPT, etc. I ask that thing to generate a picture of two working processes. One of them was meant to be called persistent homology, and I could almost get it right. He wasn't able to force it to call the other one up. So, after a few tries, that was the best option I could have. And since the other one wasn't labeled, then I labeled it. So we have two working process of topological courses of topological data analysis, persistent homology, and let's briefly speak about it. So what persistent homology is doing? Well, it is a multi-scaling variable with capture, creation, evolution, and sometimes destruction of homology classes. So once we have this collection of points, kind of sampled from something close to a circle, I mean, what we can do is to put in every of those balls, in every of those points a ball, the radius r, and then we let r vary from 0 to infinity. And as r progress, we see where r varies. So we see some small holes in plot data, for instance, over here. And then shortly after they are being put together. So what persistent topology is capturing is the first moment when you see such a hole, and the last moment when you see such a hole. And on the first one, the birth, it corresponds to x coordinate of the point. The last one, the left, corresponds to y coordinate. But this big hole over here will be present as a point right there. So if something is farther away from the level, we can consider this is not necessarily. If it's closer, more likely to be noise. This is our persistent homology. We can also look at some level sets of functions. We do the same thing, do the same exercise. Track connected components, track one-dimensional or high-dimensional cycles, and get a similar type of environments. So that's our first working course. The second one, and clear Almina mentioned it in the morning. This is Mapper. So it is persistent was more for quantitative. Mapper is more for qualitative. Given a collection of points, it builds an abstract graph whose shape resembles the shape of the collection of points, even if those points happen to be living high-dimensional space. That's typically achieved by constructing in some way an overlapping cover of our data, and then building, as we call in topology, one-dimensional nerve of the cover. Another one is abstract graph, where this corresponds to the cover, and the two elements of the cover happen to have one at the intersection. If they jointly cover some of our data points, and we put an edge between the two corresponding vertices. And this way, we're getting an abstract graph whose shape kind of looks like the shape of our point cloud. It's very vague. We are trying to make it precise. At the end of the day, what we are doing over here, we are also trying to visualize a function. And the way you can think about Mapper as well, they don't have a proper slide for it, but they just hand waving. Back in the schools, we are plotting functions from R to R. So we plot the x-axis over here, we plot the y-axis over there, and we have plotted a nice function. Mapper allows us to plot functions which are from Rn to R. We use this graph as a model of our domain, and we use a coloring scale at the top of the graph to kind of get an idea of the function. Think about the generalization of standard plots we did back in school. But two main working courses of topological data analysis. There are hundreds of people worldwide, many in this room working in this direction. And that's very good because our understanding is getting better. But also, it somehow restricts the field. So I want to think about something a bit different. I was speaking about Mapper. I will mention persistence, but I won't be the main topic. I want to introduce to you a few concepts, not necessarily new, maybe from your perspective. Some of them has already appeared during this talk, during this conference, like barrier characteristic curves. Some of them may not, like other topological tests. Pawel Dlotko was presented by Radman. And because in our work, we are really searching for real applications. We are searching for motivation outside mathematics rather than inside. That's kind of a feature of my center. I will also highlight for you an applications which kind of led us to those ideas. Okay? So we have a few three-letter acronyms. And I'm going to present starting from development of higher characteristics, and we are going back to 1758. It's essentially 15-20 years after Leonard Euler solved the Königsberg bridge problem. And what he did was essentially to range anticipation. And I think So first of all, if you study the history of mathematics, probably Euler wasn't the first who were aware of this fact. He was the first to prove it. But you know, he put many things together and he had a considerable component. And I think over here he made two new great discoveries, which lies the foundation of what we are doing now. So the first discovery, okay, so let me briefly talk about Euler characteristic. So once we have a complex polygon, and we can draw vertices, edges, and faces, pretty much in an arbitrary way. And then if we compute the number of vertices, subtract the number of edges, and add the number of faces, always get 2. Okay, what are the two great ideas? First idea is actually the possibility, the idea of building complicated, more or less complicated spaces from Lego blocks, aka from simple shapes that fit together nicely. And this idea is enormously used in essentially all the mathematical modeling, also in topological. So over here, this is the beginning of sufficient complexes. Solving Collins-Becker-Bridge problem, Euler introduced graph theory. Over here, he generalized, he laid a foundation of higher dimensional generalization of graphs. So we have sufficient complexes, and the other one was one of the first serial topological invariant, Euler characteristics. That is something that is invariantly realistic to continuous deformation. Think about Kaufman and Madonna. If I start to deform by polygons, if I do it in continuous way, no room for stretching, I'll always get the same number. And there is kind of, you know, almost interpretation from the Euler formula. So Euler number is also an alternating sum of petty numbers. So Euler number and filtrations comes together nicely. We have this filtration we kind of introduce when presenting persistent homology. Probably you cannot see this picture, but let's concentrate on this picture. We have a bunch of points. With a little bit of faith, you can see circle over here. What we do again is to put all of radius r, center the derivative of those points, and we let r grow from 0 to infinity. And for every intermediate step, we compute either your favorite simplicial complex, or we look at the number of components and number of modes and subtract from the other one. This way we'll get a number for every radius, and therefore we'll get a curve, another characteristic curve that is summarizing, that is a picture encapsulating the shape of this point. So that's a very, very simple invariant. It was kind of undermined for many years in persistent homology community. Why is that? Well, persistence has a nice picture. It's stable. So what does it mean to this? Let's take a look at the picture we have over here. So over here we have 2 points. One of them painted in blue, and the other one painted in orange. One point is very nice, densely sampled unit circle. And it essentially gives the blue persistence diagram consistent for 2 points. Perfect signal to noise separation. Orange point probably add a considerable amount of uniform noise to the points from the blue point cloud. But what we know from persistent homology is that we can construct the matching. Okay, so once we add the considerable amount of computation to the orange point clouds, we get this diagram over here. What we know from persistent homology is that we can consider all the matches between blue points and the orange points in the diagrams, and kind of maximal distance we need to move the points in order to match one diagram to the other will be bounded by the amount of perturbation within the data. So that is stability results for persistent homology. For many years, people thought that the curves, the beta curves are not stable, and yet in this they are. They enjoy the same stability property as persistent homology. Namely, over here we have again blue and orange other characteristic curves corresponding to dual points point clouds over here. And what we know right now is that such an inequality is holding, so we might completely standard L1 distance between Euler characteristic curve. It is bounded by the small constant times sum of the distances of persistent diagrams in the corresponding dimension. So that thing is also nice and stable. But we also have a number of advantages. So let's think what really Euler characteristic is. So once we have a simplex S, this simplex appears at some point of the filtration, and the moment of the filtration on which S appears is called S. So the contribution of a simplex S to this Euler characteristic curves we have over here is just an indication function multiplied by -1 to the dimensional S. The indicator function is 0 all the way to f of s, and then indicate 1. Those Euler characteristic curves are just alternating sum of those indicator functions. Very, very simple. Okay. Has any one of you been on the TDA conference when anybody spoke about multidimensional persistent topology? Raise your hands. There are a few people. So probably you remember that that's a difficult business. Persistent homology, one-dimensional filtration, it's very hard to generalize for bifiltration, multi-filtrations in general. I'd say it's a serious problem in the presentations theory are standing on our way. How about Euler characteristics? What happens if a simplex you here have the filtration, which is not a single number, but maybe a point in R2 or Rn? In this case, the simplex appears on one or a number of points in n-dimensional space. We have an obvious analog of an indicator function. So in this case, it's not one critical, it's a multi-critical filtration, so it appears at this point, at that point, those points are not comparable lexicographically. Then the analog of this Heaviside function is a function which is one everything above those 2 points. So for every point which is lexicographically greater or equal to either of them, it is 1. Everything else, it is 0. Nothing changes. I just take an alternate sum of those functions, and I get a multidimensional multifiltration for Euler characteristic. We call it Euler characteristic. And that's standard simple example where it's useful to look at 2 parameters at once. So typically in TDA, you look at the distance between points. And if you try to compute persistent homology for this collection of points, you won't see a clear signal telling you what you see with your eyes. Probably in this collection of points is something from the unit circle again, but corrupted with a uniform noise on the square minus 2 square. If we, at the other hand, start to think about the filtration, second filtration parameter, maybe that tells you the answer about the density of points, we'll start to see a clear signal. But that's why it's kind of important to make topological environments robust with respect to this type of noise. You want to see some more examples? So I call it strict paradox example. So it's very artificial example, but we have 3 filtration parameters over here. We have color, RGB, red, green, blue, and we have stripes forming different topologies. So we have either stripes or paradox. So because in this case, every pixel in that image has 3 filtration parameters, one responsible for red, another for green, another for blue channel. We have a 3-dimensional filtration. We can, first, it gives us 3-dimensional Euler characteristic profile. And very much like in the case of 1-dimensional profiles, we can compare them computing, let's say, L1 distance between them. There is a distance matrix. So let's take a closer look at this. So first of all, we see quite immediately there are 2 clusters. There's one cluster corresponding to stripes, one cluster corresponding to paradox. So kind of the topology of the black lines very well captured. Probably you can see over here that square. corresponds to a distance between this pattern and pattern. It's not as dark as the other. It means that those two are closer together than this one to either of those two. Why is that? Well, they have different topology of patterns, but they share the same color. Yet, this is something that you would intuitively expect from it. Okay. So that was an artificial example. We wanted to see how the machinery performs. We're happy about that. Let's move to something more serious. So those are histological data. This experiment was inspired by the remote paper and the authors. What they did was to take images from the prostate cancers. When the tumor is removed, they slice it, they look through a microscope and they see those fibers. And if you look at the topology of cells over here, and over here, it is kind of vastly different. And as we move from left to right, the prognosis and the severity of the tumor is worse. In order to capture it, people with histology are getting those lasers. Higher lasers have the more aggressive the tumor is. If you look at this from the perspective of data analysis, we have an image with some number of channels, and we have every image is attached. We have an attribute which is the lasers. Can we solve a regression problem? We have the histologist to get the right laser state. That is an example. Okay, so they're not looking just at the images, but they use certain chemicals to extract some information about either cell nuclei or the cell boundaries, and those chemicals are called chematoxin and gaussing. So in this case, our image happens to have two channels. It's bifiltration. So that's kind of preparing a stage for oil profile. Before we do oil profile, let's actually do a standard thing. Let's take such an image, binarize it, threshold. Let's actually make it a grayscale image in some way. Many ways you can do it. Make a choice. And then you can use a standard machine. Euler curve, persistent homology, whatever you like. And then you can vectorize it and try to solve the regression problem. You'll get accuracy of the So in this data set, this is human label data set. We don't expect 100% accuracy. As you see in this confusion matrix, the more mistakes. Say the places where human and the system disagree is between basal state 3 and 4. And there's no sharp boundary over there. This is what we expect. Well, when we go back and start to look at two filtration parameters in every voxel, then we can build another characteristic profile, which kind of look like this for the picture of this filtration. And that allows us to increase quite considerably, statistically significantly, our accuracy. So that's yet another example to show that we have more information don't found in Iraq. There are tools in topological data analysis that can be useful for you. Also, another problem with persistence, and I think you mentioned somewhere over here, is that sometimes it can go, sometimes you need a lot of memory. But those things, and policy in parallel, easy to distribute. And look at the algorithms. Build them. Don't have any problems with multi-filtration, and they are stable. Go ahead and use them. I'll show you one example where we actually were able to use it. And the reason I really like this example is because normally the flow of information, the flow of knowledge goes from statistics into PDA. And over here, we are trying to actually return the data. We are trying to bring something for statisticians that can be useful. What we are looking at over here is the statistics goodness of fit tests. So let me quickly remind you, give you a quick introduction to what we are. So essentially, we have two families of goodness of fit tests. First of which is called one sample. The second is called two sample problem. And let's start with one sample. So over here, we have a collection of points in the dimensional space. And we have a two-level distribution function. Okay? And then we are asking if this collection of points is sampled from this cumulative distribution function. This is what we call our null hypothesis, or H0. There is alternative hypothesis, which is the negation of the null hypothesis. We say, now they are not sampled from the distribution. The sample problem is very, very similar to the extent that we don't have a cumulative distribution function, but we have two finite samples of points, and we want to test the hypothesis if those two samples of points are sampled from the same probability distribution, or maybe from two different probability distributions. That's very standard task in statistics. And if you happen to have such a problem, then you may have a lot of tools available at hand. But the availability of tools depends on the dimension of your data. So if your data happens to be one-dimensional, there is essentially infinitely many possibilities. So number of Smirnov kind of instances, Anderson, Garland, I-square, Shapiro-Hicks, many more very fast implementations. It flies. For two-dimensional, we have two-dimensional data, so there are points like our samples like two-dimensional space, there are theoretical results, and some implementations from number of Smirnov AKs. There's also for cover for visas. As the dimension grows, I mean, the availability of tools is drastic. Let me tell you, last for the reference, what this most popular tool for Pomodoro test is doing today. So Pomodoro test is based on the distribution function. Here, so normally these are one-dimensional, and that's the case I'm looking at here. What we can do at every point x is we can see how much mass is actually to the left of us. So from minus infinity to x, what's how much mass of the probability distribution is over there. And for instance, over here, I think there's a cumulative distribution function for a normal distribution, which has such a nice with this shape. But we can also, given a finite sample of points, we can also do a finite sample. And then any given x, I can see what's the percentage of points to the left from that x. And this way, we can build this empirical distribution function, which is a picture in the blue. And then the statistics we are computing is not infinity distance between those two curves. The distance is large. Intuitively, we can say that, well, probably they are not sampled from the same distribution. Distance is small, and probably we have no reason to reject the null hypothesis. And we have no reason to believe that they are not sampled from this distribution. The problem with this construction is that an attempt to generalization to the higher dimension kind of needs to take into account all permutations of negative effects. This is where exponential complexity is needed. But topological variance, don't care about complexity. Let me present to you topological goodness of the test, or as we call it, triple test. Essentially, I mean, the setup is exactly what is in one sample testing kind of collection of points, and you have a cumulative distribution function. And you have H0 and H1 stated right here. Let's think about those data as really damage. So in the step one, we are building blueprint this cumulative distribution function app. And we are building a group. We are building it essentially not a problem type way. So we are growing the number of samples of the size n, so the same size as our sample in question, from the distribution. For each of the samples, we are computing weather characteristic curves. So we need to take a favorite way of problem point clouds to sufficient complex, filter sufficient complex, and then we compute weather characteristic curves for each of the samples, and we take an average of those curves. That's our grouping. This is how we expect that the points sampled from this density will behave endpoints. Okay, so we know an average, and we need to check how far away those points may be. In principle, it could use the same sample, but just to be on the safe side, we are sampling a few more collection of points from the same distribution, again on the size n. For each of them, we compute the area characteristic curve, and we check how this area characteristic curve is, how far away it is from the blueprint, the average curve. We see how far away we expect the points from this distribution to be. We are taking all those distances and take the quantiles, the significance level. But for some reason, which is not clear to me since 1950s to 30s, everybody is taking significance level 5%. So we also take the significance level 5%. And then there's the last final step to testing. We will take a collection of points, and we will try to verify H1 and H0. So we take the collection of points, we compute the area characteristic curve of this collection of points. We are checking how far away in supremum distance it is from our blueprint, which we get from this step number 1. And if this number is greater than this critical value from the step 2, we reject the null hypothesis, it's closer, and we don't have it. As simple as that. Any questions? No questions. Or let's actually see how it performs in practice. There is a question. Question, tell me. Thank you. Here we are. So in practice, it's fast. Okay. But let me see about the performance, and then I will comment on the speed, all right? How to measure the performance, the goodness of fit test? Well, there's a concept called the test power. Can you tell you what it is? So the test power is defined as a probability that the null hypothesis is rejected, and it should be rejected, and it's actually false. So we want the test power, this probability, so a number between 0 and 1 to be as close to 1 as possible. Okay. What we did over here, we took a number of different distributions. Those are three-dimensional distributions. And that's the same collection over here and over there. And for every pair of those distributions, we sample from one and we check if it belongs to the other. So when you look at this matrix, again, we want the test power to be as close to 1. It means that the test is good. It means that we want to see as much of yellow color as possible. So over here, for a vast collection of probability distribution in three-dimensional space, it doesn't need much more, but it doesn't make sense to actually show everything. We have 250 points samples from three-dimensional distribution, total number of similar tests. Average power, it's 80%. This is not test. The pattern, there is much more yellow. And indeed, the average power of total test is 10% higher. If we, and actually here are the parameters, so we put the samples of very different sizes, we put many different repetitions, and probably you can see that on the diagonal you see this 5%. That's exactly, the 5% from is a critical value over here. So quantified. This is how it should be. Test should reject the true hypothesis in the significance 1% of cases, in this case 5% of cases. And if we actually move to, so that's the same separate total test. This is 5-dimensional point cloud. So we tried to run over of Smirnov to get the matrix, this test power matrix. After 1 month on our computer, we actually built the process, we gave up. It's a couple tests, so we still have reasonably good accuracy. We don't have comparison because simply couldn't wait as long. Also, the properties of the tests are exactly as you expected. So the power of the test is growing. So if you give me more points, then I can answer the hypothesis with greater certainty. And the power of the tests, total test in blue, the total number of the orange, dimension 1, and this is dimension 3, dimension 2, 3, and 5. 1, 2, 3, and 5. In every case, the power of the tests are growing if you are giving me more and more points. So over here, we are fixing two distributions, either 1, 2, 3, and 5 for 5-dimensional distributions. The more points you give me, the better results I can provide. But in any case, especially, that's actually was quite surprising to us. Even in dimension 1, the tests are performing considerably better than co-models. So it's a statistical test. We have theoretical results. We have inequalities, which tells us identity concentration inequalities. So by all means and purposes, that's a proper honest about statistical test. It's not machine learning. We have a theory. We have to show the paper. Performance is very good. And it solves the problem. But what we are trying to do in our research, we are also trying to be as pragmatic as possible. But especially in the case for my photograph, which is extremely sharp, extremely good, but extremely pragmatic. And made a point in Pawel, you expect the biologics who came for you with a point cloud dimension 5 and tell you, well, I have hypothesis that this point cloud is something from normal with this parameter, times function with that parameter, times some other probability distribution of this parameter, tomorrow. It's not going to happen. If you want sample tests, this is what I assume that we know the distribution. So the question, in all means of purposes, is do we really need to know the cumulative distribution function? It turns out that we do not in some circumstances. Let me show you one example, which is about damage identification. So that's a project we are doing. It's inspired. We are also going to based on the data from a Polish copper mine industry. Over there, they have those big machines. They're called crushers. So the only thing you need to know that it has an input and it has an output, very much like output. In the input, you have big rocks. In the output, you have small rocks. The reason for that is if you want to extract copper, you want to have small rocks rather than big rocks. You can imagine that it's actually vibrating a lot. The problematic things is that, well, something breaks. Something start moving, something breaks. Those machines can break. So a signal, therefore they are fitted with multiple vibration sensors to stop them before something bad happens. If something bad happens. So the typical signal looks like this. Those spikes represent the times where big rock falls in and it's crashed and it's shaking. That may be a signal from a healthy machine. The problem is that if it's such a signal, this highly impulsive signal, there is a low magnitude cyclic impulse. Because that may actually be an indication that something is breaking because of this cyclic impulsive signal. Again, the problem is that the amplitude of this signal is very small compared to those peaks. Typically, we cannot see it. Question. Can we use Topological? The answer is yes, because those machines are normally operating for many years without any problem. What we needed to do in Topological was to construct this blueprint, kind of, it's a surrogate for quantum distribution function. We have a lot of data from healthy machines. We can use it to construct the blueprint without having absolutely no idea what the distribution of data systems. That's essentially what we are doing. The rest remains unchanged, so that's essentially I just said it. Then we start to compare. Is topology bringing something new to the table? So on this slide, they use CDB method, which is essentially quite a high-end spectral method to identify those cyclic impulses. And over here, we are testing it on some so-called alpha stable distribution. One thing, we are using Venn curves rather than Euler curves. I can guess may allow you to guess why. Remind me to tell you at the end. So we use Venn curves and alpha stable distribution. Over here we have two parameters. Alpha is the measure of impulsiveness, and over here we have a measure of cyclicity of impulses. So the more that's the amplitude of the cyclic impulses. So the higher the impulses are, the more probable we are to actually detect it. But we want to detect it for all value of cyclic impulses and even in the presence of large numbers. And that picture often shows that the total tests performs better than the spectral methods. And because we are working with practitioners, they actually made tracking over here. We were able to do the tests as well, in a broken situation on the test bunch. So I'm not showing you the matrices because we are not, of course, able to get as many data as in the theoretical case. Another important thing over here is that over here the engine can rotate at different speeds. And the healthy cases, if you look at PCA projection, we took first principal components of the vector pairs. They're located over here. And then the case in which there is something wrong, and they're located in different regions. So once again, we get essentially 100% accuracy over here if we plug it into SVM and something very simple. But our collaborators are actually working in mind. So those are the data where one of our collaborators went down into the line. Because we're very high-end recording tool to check we do the noise of the bearings. And our task was to detect if the bearing is broken or not. And once again, CVG is so pretty much in the hand of the smartphone. So you guys making the that's the level of the sensor. CVB is getting essentially 80% of accuracy. Topological methods are 92, but there's nice message over here. So if we combine topology with spectral methods, we are getting considerably higher accuracy. And I think that this should be one of the messages we get for the community. We are not providing a silver bullet, but we are providing an important addition can be incorporated to existing files. That's how we are doing it. I have one more thing, and I think I will on time. So Rodrigo spoke about bone upper. I want to give you one more fun example, and I want to ask you one question. So just to remind you from the morning, it's been a long day. Bone upper is a way to takes is an algorithm that takes us an input collection of points and which returns an abstract graph, shape of which should resemble the shape of this collection of points. How does it do it? First of all, we construct an epsilon map. So we select a unitable length. Then we choose a subset of points that are called over here. And they have the property every black point, every point from our initial sample have a colored point not further away than epsilon. Okay? It means that I take walls of a radius epsilon, put them center at every colored point, every point from my epsilon head. I'll get a cover. Then just normal things as we do. Computer one-dimensional nerve.
How do you find this epsilon net, and how do you know how many points?
So there's a Greek algorithm that says essentially the furthest for something. So first point on my epsilon net is selected at random. And then I'm looking for all the points in the radius ball epsilon. And they are out of the game. And if there is still some point which is not covered, then I take the first point which is not covered, look for all the points in the radius ball epsilon, take them away. And eventually after a finite number of steps, bounded by the size of my point, I'm going to get the epsilon.
You determine the epsilon first, and then it tells you the number of landmarks you need.
So you really need to look at the number of parameters. Although we are looking at a few techniques that may allow you to choose it automatically. But at the same time, if you look at the data sets which have some fractal structures, and you realize immediately that there is nothing like that as much as an epsilon. So depending on the features you want to see, you may have very different ranges of epsilons. And think of so basically around that type of stuff. So depending on the resolution, you are going to start on the different levels of resolution. And therefore, we never actually enforce any strategy. We never seriously enforce any strategy like that. Make sense? Okay. More questions? Right. So So I promised you a test. I know it's Saturday evening, but the prize will be for those of you who bought the tickets for the dinner, we're going to dinner. So for those of you who didn't, wow. I have 5 minutes. For those of you who didn't come to class, lucky cat, right? Everybody who likes Asian food probably knows it. There's a standard experiment. So imagine I take my lucky cat and place it somewhere. Then I take the camera and start to take pictures of lucky cats from different angles. And then I move all the way around. I cannot move because there's a thing. So I'm getting this number of pictures of lucky. In this case, I'm taking quite low resolution, 128 by 128 picture, grayscale images. And then I simply flatten the image and vectorize it so that every image corresponds to a point in 16,824 dimensional space. So I get a collection of points. A point cloud is 16,384 dimensional space. The question for you, you answer in the linear provided that you take, or is what's the shape of the point cloud? So we are speaking about something very high dimensional. Would you, yes, go ahead.
The cat.
Let's try. Circle. Okay, why? Exactly. So what would happen if the cat has some symmetries? Okay, it doesn't, right? But the answer is correct. So think about it. Okay, we are looking at the front face, vectorizing. Then I'm starting slowly to turn it. So that picture corresponds to like one in this 5 dimensions. So I'm starting to turn it. I turn a little. Do I look very different like that? Not much. And, those points are pretty close together. But as I start to turn more and more, I'm starting to look different. So I'm moving away from my initial position until I come back on the other side. And so you understand, it took some effort to understand the shape of the point. If you just load it to the software, there is almost anything. But there's something more in this. Take a look, tell me, is there anything that bothers? Yeah, there's some asymmetry, right? So this graph over here is kind of more dense. There are many more connections. Why? And again, if you are using the software, you can just click on the novel and you'll tell you which picture it's coming from. It's not that easy. I mean, we need to exercise a little bit. Tell me, what's the difference? What is happening? Why there is asymmetry? Exactly. This is the front of it. So, excuse me, if I want the back, and I kind of look the same. I need to rotate quite considerably for you to see a difference. But then in the front, we have many more features, and therefore, smaller rotation gives a considerable distance. And that's exactly what is happening here. So, PDA as a tool of data analysis is used essentially everywhere. So if Simon looking at a collaborator in finance and economics, we looked at that thing which is called Brexit. So that is actually an interesting data set. No. We both know. Remain. Remain, please. Yes.
Which technique do you use in the previous slide to project your 16,000 dimensional space to Archie?
Which one? I never projected. I just built it this graph. That's precisely its construction. This is a 16,000 something dimensional point cloud. I'm creating the slow next, looking where the balls intersect, and here's the result. There's a difference compared to what I call the conventional mappers. This is a gamma and Topological and Georgia. Okay? Any more questions? Let's go to Brexit. So, you know, this was the time I'm not in the UK anymore. I decided to leave. And it was the time when I was coming. And I was actually having an interview exactly on the week of referendum. That was anyhow. Well, people expected 52 to 48, but for Remain. Happened that the result was 52 to 48, really 4% of the error. That's big. I mean, we know that statistically it shouldn't happen. 4%, that's very much. In this continent, you have a similar, let's call it accident. It's hoping will not happen again a few months later. Putting fingers crossed without anybody. Okay, what do we see over here? So in every country, every 10 years they are doing census. They're asking you all sorts of questions about social status, income, education, possession, etc. And we integrated the data from 2012 UK census. And we superposed on the constituency level the result of Brexit referendum. People, they want to leave. And if we look, we are looking at, we selected like 30, 40 answers in the census data. And you can look at the paper, but they are about the income, they are about the education, they are about the self-assessed health, self-assessed happiness, etc. People who want to live are very homogeneous in this space. People who want to remain are very heterogeneous. If you want a more detailed study, I mean, there's Scotland, there is London area somewhere here. There's a lot of stories you can tell, and actually, you know, based on those visualizations by colleagues in sociology, they actually make the stories, they come up with hypotheses. There's one more thing. 2011. Will Brexit happen or not? So, Boris Johnson is checking. Boris Johnson is calling for a general election. At the same time, this guy, Jeremy Corbyn, is pretty vague about whether it should be an additional referendum or not. After the election, what happened was that there was one of the biggest failures of the Labour Party in the, let's say, post-war history, which is kind of predicted by us. So a few months before the election, we posted that the UK is changing Europe, an article based on those visualizations saying that, well, if you look at the people who supported Brexit, right here, they also support Labour Party. If you are vague about your stuff, probably you are going to have problems in the elections. And here, you know, inspiration may be coming from very different angles, medicine, biology, but also to mathematics, and I want to refer back to Amila's talk. So those tools can be used to compare different high-dimensional data sets. Those tools can be used to look at the data of symmetries, number of possibilities. I wouldn't be able to do any of those without a fantastic and dedicated team I have in my district center. Justina from DICE doing dynamical systems. Davide over here and over there are working with Martha Bachmann. We are working on the shape of neurons. Ivana Stazus, phylogenetic. Matthias, we are working on, let's say, also marker development. Simon Lupin, economic finance, Brexit guy, macro statistics. Niklas statistics, and also the mining industry. Example, Michal is doing dynamical systems, Jan, processed surfaces, Bartek is working on cryptography group. We also are very happy to have online music as a mathematical professor. And I can recognize this person over here in the audience. Great to have such a team, and I'm extremely grateful to them and for the funding provided. Okay, so that's the part of the scientific. If that's okay, I want to speak for 2 more minutes. Because that's the last one, the conference. And the conference is here because of GeoTopI online seminar. So more than 6 years ago, Carlos was putting together this initiative. And I organized a few conferences with that. And I know how difficult it is to organize. Yet, after 6 years, keep in mind, there are essentially 2 online seminars in applied topology. There is AAT and R, Lori is also doing a lot of this. There's Geog of A. Requires a lot of attention, a lot of stamina to get very good speakers, to keep it working, to keep it flying. That's thanks to many people, but thanks to Carlos.
20 years ago.
Some people so as Carlos mentioned, we met for the first time at INRIA, and I also postdoc from the fractional groups. Now I progress, I have my own group. And I understand how important it is to take care about students, to organize such events. And I know how difficult, how much time and attention it is doing. This is taking. And I see Carlos doing it, supporting students, organizing events, making the community live. And there is one thing, only one thing I can say. Thank you very much. I think that's extremely important. Oh. Go ahead.
Thank you. No more questions or?
I'm not done yet. I'm not done. There's still a few slides. Look at this curve of the line. Thank you. Very much like in my case, nothing will be done without a dedicated team. So let's thank all the organizers. Thank you very much for the fantastic job of the great and I love that. So, once people are playing with artificial generative artificial intelligence, 6 years. 6 years, more than 6 years right now. And they wish you to say happy birthday. They wish you to be happy during this one day. In Poland, we're doing it better. We say 100 lat. 100 means 100, lat means years. So we wish you 100 years in good health and happiness. And I think, I think in Spanish, that's what we should say. I wish that, I hope this seminar flies, stay for very long. You're doing a fantastic job. Thank you. And I think I'm speaking for everybody to say, well, we had a great time over here. Now I'm done. Thank you so much.
It was beautiful, but are there any more questions?
Straight to business. How many more questions?
I would rather say curiosity, but this work that you are doing, center, what would be the next most, I mean, the most decided application that you will do to do now?
I mean, in our center.
Right, in your center.
I have 2 kids. If you ask me which is my favorite one, I would say I'm not going to answer this question. I can give you the list. Which one will fly the most? I do not know. So I'm sorry, there are questions I cannot answer. I do not know which one is the best. Of course, everybody has the favorite one. Everybody has the favorite children. But we don't say which one it is. Right?
Yep.
And I will also not say anything.
Yeah, I think that you are like me when they ask you, which is your favorite children? I don't know. So,
Yeah, I love them all.
so thank you very much again, Pavel.
There's a question.
Is there a library, home mapper?
Is there what?
A library.
Yes, there is. Absolutely. PB install PI ball mapper,
Oh, okay.
UI, Python.
Is it Python? Is it in Python?
Yes, it is. There's also in R with bindings to C++.
So, one question about ball mapper, I think I already asked you this question once. So Python just take a random point and start doing the scoring, the coding with that some bolts. So if you run it twice, you can have a slight different covering.
Correct.
Is there a way to just get always the same output, like a way to define it? Doesn't require that it's always same.
No, I mean, there is a stochasticity in the process. However, I can spoil a little bit. So what we have in an ON right now is a statistical tool. So we want to compute an average output mapper, or we want to sample many times for different epsilon nets and give you different classes of mapper graphs that you get. So we cannot solve the problem, but we try to circumvent it, and then the paper should be online at some point, hopefully this year.
Oh, awesome, thank you.
Any other question? Oh, no, really, thanks, Pavel.
Thank you.